this is showing the counts, of some of this stuff. But that physics letters A, volume 210, pages 382 to 390 is, here's another one. They have also seen tritium, and this is documented in an earlier work in Fusion Technology, volume 33, and this is, showing them the concentration of tritium and so forth. And then, of course, the biggest thing is the XSD. And this is showing the, watts versus time. An important point is that they can turn this thing on very fast. Typically in cold fusion experiments, it takes hours, even days or weeks in order to get the effect to turn on. And because it is a Navy lab, they were able to they have the equipment to do IR imaging, and they see these hot spots, really, sort of very spectacular structure. And the hot spots can be extremely high in temperature, thousands of degrees, but over very small distances. And again, this is documented in a 1999 paper in the Wave-Smith building. It's been very hard to publish things in this area because of the controversy initially. Things are beginning to change. Now, the most recent stuff, which is really mind-blowing, involves applying these electric fields. They electrodeposit palladium onto a gold electrode, and here are the currents that they use. It's small, it grows, and then they increase the cell current up to 30 to 50 milliamp for like 2 hours. And then they apply an external electric field, and they increase the cell current to 100 milliamps. They terminate the experiment after 48 hours or more, and this shows the basic geometry. And they get incredibly interesting morphology changes. These structures, and they can examine these structures. All right, so here you have structure in the absence of the electric field. You have these cauliflower-like morphology of globules. And then, well, anyhow, this is just the same kind of thing. So there are minor deformations. After you apply the electric field, you get these dendrites. And these features are the result of the combined action of the current flow through a porous structure, the evolving deuterium, and the electric field on the separated microglobules suspended in the electrode restricted by the porous structure. And you get these elongated structures, and it's fascinating, actually, what goes on. And the thing that's really sort of neat is some of these correlate with the apparent appearance of new elements. That's something that people don't realize. This field is not cold fusion. It really is low energy nuclear reaction. And there's even some of these morphology changes. There are interesting similarities between structures that Russ George, who's going to give a talk later, observed in other experiments involving an entirely different procedure. And there'll be another talk on this too. And the features are suggestive of solidification of molten metal occurring under a liquid, some kind of melting kind of effect. The energy needed to melt metal is of a nuclear origin. It should be reflected by chemical analysis of these features, and it did. There were blisters. Chemical composition of a detached thin film blister, so there's a blister. The analysis of the blister shows the presence of calcium, aluminum, silicon, magnesium, zinc, gold, oxygen, and chlorine. The gold, oxygen, and chlorine are present in the cell components and have to be attributed to nuclear events. The distribution of these elements is not uniform, suggesting that their presence is not the result of contamination. Conclusion. Oh, that was fast. An external electric field changes the shape of the individual globules of the cauliflower structure of the PDD co-deposited material. With the shape change, there is a change in the defect's density as well as in the stress field intensity. Both of these factors affect the interaction between the D+ complexes and the PD lattice and contribute to the formation of the PD. And it looks like there's some kind of self-organization. It's a complicated thing, domain. The concentration of the D plus complexes is determined by the overpotential. The effect of an external electric field is minimal. Excess enthalpy is generated by highly energetic, fast reactions that resemble mini-explosions. This view is supported by the IR imaging, the hot spots I referred to, by the response of the pressure and temperature-sensitive substrate, piezoelectric material, onto which the PDD films are co-deposited, and by scanning microscopy examination and analysis of the selected isolated spots showing elements not originally present. The triggering activities to initiate fusion reactions are located within the first few atomic layers and most likely involve changes in the electronic structure of this region. These changes are transferred deeper into the PD lattice where the nuclear events occur. The nuclear events to form tritium, helium-4, silicon, calcium, magnesium, zinc, aluminum, etc., are of the type precursor plus trigger unstable nucleus stable element. So there's very minimal high energy particles in all of this. Okay. Hokkaido University. And George Miley is, of course, at the University of Illinois. Okay. Now, this is the thing I mentioned. This is a very clean experiment. The information is available through a refereed publication, the Japanese Journal of Applied Physics. It came out in July of 2002. It's work that Mitsubishi Heavy Industries did over more than a decade. The experiment is quite remarkable. They evacuate everything. They do photo emission. They systematically see atoms of cesium disappearing and atoms of praseodymium appearing. That's the addition of 4 protons and 4 neutrons. This is a rare earth. It's an extraordinary experiment, probably the cleanest, best evidence that you are getting, for a physicist at least, that low energy nuclear reactions of an absolutely unbelievable nature occur. Key thing is the materials are very well controlled. Now in this paper, he's actually interpreting these. There were other things that he did that are not as clean cut as this, but there's the idea of, he talks about cluster reactions. Now, as I say, it's all speculative. This is a very new field, and it's complicated. This is a remarkable thing that he did, where he systematically did the electrolysis and examined the materials that were accumulating on his cathodes. And 30 isotopes, the ones above this line, these exceed the maximum impurity limit. It's a careful experiment from the electrolyte. And there appear to be 2 peak fission. They actually appear to be fission products without any high energy particles. It's got to be something cooperative, and that's what he talks about. And so forth. So the gist of his talk is dealing with this. So I won't go through all of this because he gave me too many view graphs, but I'll get through a lot of it. So he's going to talk about basis for complex nuclei, clusters. Evidence, and it has to be a cooperative effect because there's no high energy particle. Evidence for cluster physics. And then, well, I actually showed you those were his transmutation experiments and the notion of a fission complex and associated energetic. The Lipson superconductivity, in the case of palladium deuteride and palladium hydride, is actually evidence of a superconductor, which is really bizarre. You have to get high loading. Part of this is the high loading of palladium deuteride is not very well understood. And then he has some evidence of X-rays coming off from cluster locations. Even potentially, he speculates they're coherent and they may be actually lasing. And then the Iwamura experiment, he had some modeling of that. Okay, so they're dealing with this FLAPW, the Vienna 2K code, and they've made some calculations that really have excited states. And actually, the FLAPW, this is work in progress. The excited states, nobody knows how well those calculations do in terms of computing structures, but the eigenvalues are probably pretty good, so that's not too bad. And they've improved their approach over earlier studies to understand the electronic behavior. They use a standard GGA approximation, and I really won't show this. This is just really telling you where they're going. So this is really much a work in progress, but part of this is also to tell you what they're studying. Their model is to say, okay, you get like 3 deuterons in some kind of lattice imperfection site, and things get bunched up, and that's the nature of the reaction. But this is speculative. There are other theories, I would say more refined theories, to talk about this. But they deal with what they postulate as a swimming electron screening model, which allows sufficiently close approach for intersecting trajectories. A key point that, regardless of whether this model is real, it actually works. It got them to think about interfaces, cracks, and this sort of thing. And then they subsequently found that that guidance helped them. And it turns out there's good reason to believe that nanostructures, nanocrystalline effects, cooperative nanocrystalline effects could be playing an important role here. And so then they view things in terms of some kind of conservation of angular momentum rule that may be involved with the cooperative effect. And let's see, this is referring to, they're not allowing the structure, the imperfect structure to vary. So they maintain that, and that's partly because of that. And then they compute these sort of large energies, excited state energies, and what's happening to the inner core electrons, and they suggest that of course is the origin of what they're seeing. Okay. They say, based on their model, that the reaction product array is explainable by cluster physics. Now, I know that they've published some of this stuff, and this relates to the idea of nanoscale features. A lot of mainstream physicists would say this is garbage. And I would say it's speculative, but there could be reasons for cooperative effects that may make that work. And the calculation of the binding energy that they get appears to be consistent with what they've done. Okay, and this shows a plot of, the different energies and so forth. And to really understand this plot, I don't understand this plot, but to really understand it, you should contact George Miley. Now this is interesting. Lipson et al. Found evidence high temperature, I think it's 30 degrees, superconductivity, and hydrogen cycle TD indicates there's a super stoichiometric HD cycle. Well, what they're talking about there is cramming things in somehow is affecting the dislocations, or affecting the electronic structure in such a way to induce superconductivity. Most people don't realize that at high loading, force loading, palladium deuteride, you can get this. The conventional wisdom was done at ambient pressures at low temperature. It is known that palladium deuteride is a superconductor. It superconducts at 11.5 degrees Kelvin, and palladium hydride superconducts at 9.5 degrees Kelvin. And that's an anomaly, actually. Normally, when you increase the isotopic mass of something, the superconducting temperature goes down. But there are, some theories that sort of explain this, but the fact is they're based on phonons, and in these systems, the notion of phonon gets a little contorted. There's very strong electron-phonon interaction. So under electrochemical, anodic, and/or H2 gas cycling, you can reach. I don't know what that is. All right. Well, so anyhow, it's a complicated system. I guess that's the bottom line. And they have been speculating about, particular geometries, and they tried particular geometries, and they got agreement, I think, when they jammed in about 3 of them. But the key point that this is showing the Meissner effect. They had DC magnetic squid measurements, and what you see here is this is PDH coming up like this. These are round circles with PDHX. But basically you see an expulsion you start to see an expulsion of magnetic field around 30 degrees. Okay, so I'm almost done. PDHX and PDOHX samples after H cycling and annealing at temperature 573 degrees K contain only condensed H phase inside deep dislocation cores. X is the concentration, the amount of H per PD. And when I talk about full loading, I'm talking about 1 H per PD. And okay, so the X, the overall amount is this, but in dislocation nanotubes, it can be as high as 3. And that's what I was saying. Yeah, that's right. They postulate it's a nanotube structure. It's Twin measurements show a weak type 2 superconductivity involving cores below 30 K, so it's about 30 K. Both magnetic and transport measurements suggest superconducting transition below 70 K. And reproducible Meissner effect is obtained at H, this is the magnetic field, less than or equal to 1 Oersted in an AC field. That's bad notation, it's H in both places. Okay. All right, so that's the basic part of their talk on this. There is evidence that to show the X-rays. There's evidence that you can get X-rays out of this. All right, so that's the end of the talk. Are there questions? Thanks, George. I find it funny, but no. The output is the red line. The input is the blue line. And you start seeing these kinds of effects. Again, it's about 70,000 seconds. And this is milliwatt. So it's not a large signal. And that's been a confusing point initially. Sometimes you do get large amounts. Okay, so the heat effects are observed with D, but not with H, under similar or more severe conditions. And these are very careful experiments. Okay. Excess energy of 2.1 million megajoules, 80% of the input, corresponding to 1,200 megajoules per mole of palladium. So again, this is, you can't see it. You mislabeled them, but En is this. Oh yes, now you can see it. En is that. E out is that. I don't actually know what E net means, but this shows the output power and the input power. This is the second laboratory. They provided the electrodes. This is this group, Energetics in Israel. And because they do this extraordinary thing where they have this remarkable waveform. Now, if you notice, if you look here, the input power is really low, and they get this tremendous signal. I mean, this is like 40, 25 factor. And they also have some tritium. So the excess energy of 1.1 megajoules, 25 times the input, 2,500%, corresponding to 400 megajoules per mole of palladium. Astronomical figures. Excess power at SRI, 30% of input. And this is just the ENA foil from palladium. The SRI people have done monumental work. And they don't have a talk here today, but if you go to the www.lenr C-CANR website, or lenr.org, www.lenr.org, you can look for Michael McCoubry, and you can look and see the spectacular work that these people have done. It's just, and there's more. Okay, I just put this up because they found they had 3 excess power over 10 experiments. That's not a good repetition rate, giving with high D loading, D per PD greater than palladium 0.9. In some cases, also with less loading. They've been observed at ENEA. That's less loading on the average. That doesn't mean that in clusters you could have as high loading. And there's good reason to believe that there's a high loading criteria. We can conclude that high D loading is a necessary condition for excess power production during loading of PD with D. But they're just, well, they went to this idea of using lasers on a particular motivation, but Dennis Cravens, I didn't mention, he also has used lasers. And the idea that there's a collective electron oscillation could have a key role in low energy nuclear reaction processes, and that the need for a proper trigger has been introduced to create certain plasmons, polarity. So they do some laser triggering. And this is just one sample. They had like 4 experiments. I can't show it all. But what they have is the output energy, the input energy, and a change in energy of 30 kilojoules. And you can see that it's here. Most of the signal is here. And look at the time. That's 400,000 seconds. 600,000 seconds, you know, these are many hours. Yeah.
Where in the time scale are the laser pulses being applied?
I assume here, I don't know, you have to really ask Vittorio, and you can write them, he'll tell you. But I assume they were probably turned off, and you know, the thing's tracking. I mean, the blue of course is the input. And of course, they've done some nice mass spectroscopy work. They can clearly resolve their helium-4 peak from D2, and they can also resolve HD from helium-3. This is a very well-funded group. Okay. And for mass 2, too. Now, this is a typical thing. They find the expected value of helium-4 based on DD fusion. The reaction is 23.8 million electron volts of energy released. Typically in normal fusion, that's released in the form of a gamma ray. This is released, though, in the form of heat. Now, it's very typical that you'll have slightly more helium. That is, you'll find, or rather, you won't find the signal. You'll have slightly more energy than you expect. But what happens is this lack of energy. Yeah, you get more energy than helium that you find. And so you find slightly less helium. But this lack of it is helium that gets trapped in the electrode. And the people at SRI did a systematic study. It showed that it's quite believable. And you know, it's clear that that's what happened. This is well above background, and that's a typical kind of signal. So you get within about 50%. Okay, so the expected amount of increasing of helium-4 is in agreement with the energy gain by assuming a D plus D equal helium-4 plus 24 MeV reaction. Helium-4 stripping from cathode increases the correlation with produced energy. In other words, if, for example, you recycle deuterium through the sample afterwards, after you've made these measurements, you find helium. Oh, shoot. I'm going to do that. He's got such a complicated PowerPoint, it takes a while to load. Okay. Now, they also have found, here, let me go to this. They found helium at SRI, too. And again, this shows this was a monumental experiment where initially they found 62% of the helium they expected. But then they put helium, then they recycled deuterium in it, and they got it. You know, they were noticing that they were getting additional helium out, and then they put deuterium in and they got it. So the helium-4 concentration increases into a cell giving excess power. Helium-4 stripping from the cathode makes the correlation with produced energy satisfactory. So this is where they're doing the stripping. Dave Nagel said, this is real science. And of course it is. And you're finding byproduct. Conclusion. More heat effects are observed with D, but not with H, under similar or more severe conditions. Heat bursts exhibit an integrated energy at least 10 times greater than the sum of all possible chemical reactions within a closed cell. Experiment reproducibility was significantly improved as a result of material science study. That's how they were able to give. I didn't show that. He's got some photographs that show they did some, you know, a bunch of different things to the materials, and they systematically looked at the effects of annealing and other things. Conditions are required to have reproducible excess power. A loading threshold of D per PD greater than 0.9 is necessary. Suitable material is required to have reproducible heating above the threshold. Triggering through things like lasers is helpful. Suitable status of the material to have coupling with trigger. So you have to get this right, and you have to systematically do it. 3 excess of power over 3 effective experiments have been achieved by doing this. So 3 out of 3 following these things, they've done it. The same material is allowed to, that's used to reproduce the effect into the 3 different, they gave this thing to 3 different institutions and did it. The agreement between the amount of helium-4 and produced energy seems to be a clear signature of a nuclear process. Well, I'd say it's compelling. The condition of D to PD greater than 0.9 has been fulfilled by electrolysis, I guess, probably because of not homogeneous loading. Yeah, that's what I was saying. In particular plate, you know, the stuff can accumulate. Okay, so that's their stuff. That's thanks to and not others, and that's true of our model too. And he talks a little bit about this Oriani-Fisher experiment and has some conclusions. This is a bizarre experiment, actually. And I don't know. I mean, I don't even know if it's real. It seems like it probably is. So, Peter has a theoretical effort for 16 years to understand anomalies in, what do you mean? Oh, metal plus deuterium. His recent focus has been on phonon nuclear coupling mechanisms, coherent phonons. Schwinger also thought of this idea. We have a variant of that idea. Ours involves charged states, ion band states, but phonons. Resulting models, and there's a strong electron-phonon interaction in this system. So the idea of having some coherent coupling is really quite mainstream, actually, although nuclear physicists don't realize that. The models can be derived from the generalization of what a well-known procedure is called the nuclear resonating group method formalism that was developed by John Wheeler back in the 1930s to include the lattice. And you know, Wheeler didn't do that. Nobody thought that that was appropriate. So in the lattice group method, you generalize the resonating group method to include lattice effects. So in the standard situation, you write a wave function. It has functions that depend upon angular momentum and channeling and so forth, and basis states. The optimization, and this has just been done at the nuclear dimension, typically, but he is going to include coordinates associated with lattice. So the optimization of the lattice channel separation factors, these are these things. Well, no, actually, no, you differentiate with respect to that, I guess that's right. And you get a couple channel equations. You can also derive this using another formalism called R matrix theory, and I'm going to talk about that in my talk. The new formulation now includes lattice effects on an equal footing with a nuclear problem. And yeah, and Peter, this is available online, Proceedings of ICCF8. It's available at www.lenr.org. Now, an important thing that when you start thinking about the idea of cooperative effects, you start thinking about the idea that something happening on one lattice site can affect something else. So this is what he refers to as site-other site reactions. And so the model predicts that reactions at different sites can be coupled together as a second or higher order reaction. And that's possible. That's certainly possible. And you don't have to have high energy particles. I'll talk about that. Now he wants to address the, there are other things. There is evidence of alpha particles being emitted. And that's in a different experiment. And this is the work by Andre Lipson. Again, it was, I think this was regular loading, I think. That's high loading. Here he says there's a null reaction mechanism. In particular, when he's trying to find the alphas. He has a hard time finding slow alphas, but he can find high energy alphas. So the models indicate that the helium-4 dissociation through this mechanism leads to products that have trouble moving apart. Hence, they might be observable in an experiment. And so he has particular things, and this was his early proposal for site-other site reactions. So you're having an alpha's getting created, and then it's actually separating, and it can excite other things. Now there's another reaction that he's investigated. Peter is very much involved with examining this experiment by Kasagi. Kasagi observed evidence of multi-particle reactions, and it was a very sort of, he had these titanium gas-loaded substrates. He found protons coming off. So in other words, he put in 70 keV deuterons, and he found 21 MeV protons coming off. Now that's bizarre, and he wanted to understand that. And so he interprets that in terms of compact states. It's interpreted as D plus this compact DD that came from a helium-4, giving rise to a neutron, proton, and helium-4. And then he has these other things where helium-3 can accumulate in the target. And then a normal form of fusion. This is a standard form of fusion, except the energetics is different. It's followed by the helium-3 combining with a D, giving a proton in helium-4. So he's investigated. If you string all this together and you think about what he's saying you have a 2-particle reaction going essentially into a 3-particle reaction, going back to a 2-particle reaction. And all of these things, this is not impossible. You know, it's just not ordinary DD fusion. And so here's another example. He has these compact states. The helium-4 forms like a virtual DD, or even a molecular state, and you have neutrons and helium-3. So many states can result from this unstable kind of picture. And so basically the phonons are what are doing this, but he's getting all these different possibilities. And it's pointing to the fact that this is complicated stuff, and it is, and he's absolutely right about that. Helium-4 going to neutron plus helium-3 to a DD, and this, what he means here, different angular momentum. SU3 is referring to an L equal to 1 kind of angular momentum from different spins. And you can get SUN. You start thinking about all these different nucleons potentially combining. That's the basic idea. So, SU3 model shows coupling between nuclear and phonon degrees of freedom. Simple model also shows coherent enhancement effects. Simplified model is amenable to calculation, however, rates are predicted from this model. Not fast enough to be relevant to heat effect. Yeah, he doesn't get the heat effect. That's something we do get. But then he goes on to newer models. Again, a much faster rate is predicted if polarization is induced in neighboring nuclei. Here is depicted a model in which the initial transitions from the molecular D2 state is coupled to excitations in the PD nuclei. That's the and it gets into this idea of angular momentum exchange. We observed previously that the Dushinsky, this is an old method, mechanism, this is a mass defect method actually. It can produce phonon and angular, in other words, you have unequal mass things. Phonon and angular momentum exchange for the mass 4 system. The same mechanism also is expected to work to produce compact states of heavier nuclei as long as a neutral partner is made. And here he shows the Dushinsky mechanism for PD. You have PD in an initial state, and then you have this sort of, it's trying to interact with the neutrons in the final state. And it looks different to the lattice because it's got a different mass. And this difference in mass creates and you get an acceleration effect that can be maximized, and you can get neutron clusters, suggesting neutron clusters. But they're staying inside the lattice. And then he goes on, there's a coherent excitation transfer, and a large acceleration reaction that can be transferred from one population to another, and so forth. I'm going to skip to the conclusions, I think. You have neutron clusters. Oh, I will mention this one thing. Oriani and Fisher have this really bizarre experiment where they do see, what they see though appears to be, they put their detector in a place where it just really, you can't explain what they get, and you really have to look at their papers to do this. The ICCF 11 paper by Oriani explains this. He finds large amounts of alpha particles in a place that is removed, essentially from, well, he does it here, it's in the bath, but they actually take it out, and they put it over here, and they find alpha particles, so they don't really understand why. But it's... he's saying neutrons, but
Okay.
There's this neutron? I guess maybe it's neutrons.
They're looking at neutrons with that not alpha.
Okay, with the CR39?
Yes.
All right, okay, well, I'm not an expert on that one. But they have a very weird experiment. Anyhow, I'll just go through this. Oops. God, well, there, I missed so many conclusions from there. Okay. All right. Ongoing theory effort to develop models relevant to cold fusion experiments. The coupling between lattice and nuclei produces other side effects. The model is consistent with large number of experiments. Polarization of post-lattice nuclei leads to large rate enhancement if it occurs. The Dushinsky mechanism for angular momentum exchange favors the formation of neutron clusters. Neutron cluster release predicted when excitation is interrupted. The observation of neutron clusters reported by Oriani and Fisher, similar by others at ICCF 11. Advanced state theory. Okay. Now he says, theory must explain Fleischmann-Pons cold fusion, the Iwamura transmutations. That's the stuff where you have cesium going into praseodymium, and now he actually refers to the Oriani MEV alphas. On the he says, so there's some disagreement there. Hagelstein says they're neutrons, but he says they're the alphas. Now, I don't think there's one mechanism that explains all of these things. I think these are complicated things. Talbot seems to think there's one. Now, there may be one kind of guiding principle. And he says there's a common requirement of what he calls coherently partitioned block D+. Now, this idea, partitioning, that's saying it's waves. He's saying that you get D+ ions in waves, reminiscent of electrons in waves. And then the notion of double block symmetry reduces Coulomb barrier. Well, this is really a statement that in a many-body system, you can get approximate, in particular situations, you can get approximate symmetry between a configuration involving two coordinates, block-like symmetry, as in solid-state physics. And that this fractionality associated with the additional degree of freedom and giving it block symmetry will give that. There actually are ways of explaining this in terms of formal scattering theory where you don't even have to talk about that terminology. Basically, that it's a many-body state. But the picture that he has is you have charge density distributions. You start out, you think of ordinary, here's two Ds, right? There's a D here, and they could be in a molecular state. Now, you can also talk about a situation where you have I should be showing, well, comments, he did make comments. A D+ block state, and so you have the Ds, and they're distributed over a lattice. And what we're really talking about is one deuteride interacting with, for example, fully loaded palladium deuteride. You would spread it, and the idea is that it begins to behave like an electron. Now, the electronic structure actually is conducive to that sort of thing at full loading, but that's another topic. The way he likes to think of it, though, is this way. And it's like a dimpled metal sheet. You can get, an important point is you can get discontinuous changes in momentum that allow for overlap. Nuclear physicists haven't thought about that very much because momentum is not mass times velocity. In a solid momentum, the momentum that one has in the Heisenberg uncertainty principle, mass times velocity is momentum minus E over CA, where A is the vector potential. And the point is that the A has a constant value, a zero of A. And that is actually that's not thought of much at all, because you're normally thinking about dynamical processes. But in defining that A, you can get a large change in A, accompanied a sudden change in A, accompanied by a sudden change in momentum, as in the Mossbauer effect. In the Mossbauer effect, you have things rigidly moving, and this sort of thing. And this is actually very much closely tied to the nature of solid-state physics. Talbot has expressed these things in terms of a simplified sort of quasi-particle picture, but there is rigorous quantum electrodynamics in this. So anyhow, he postulates that the energy of coherently partitioned nuclear products are there, and they are affected by the degree of partitioning. In other words, if you have a lattice that is a certain size and well, what you normally would think of as a high energy at one location can be at many locations. And so the amount that you would have at an individual location could be proportional to 1 over the number of unit cells, as in a Mossbauer type situation. And he writes down a Hamiltonian associated with this. He has a piece associated with a conventional lattice, the center of mass coordinate of the particles, and then there's a separation variable, and this is the way that he treats the Coulomb potential, because it's really, in a more realistic situation, what you're really talking about is what sits inside a matrix element and involves, this really one is dealing with a Dyson's equation, and this would be the dominant portion associated with the Coulombic interaction when you had the wave function associated with the 1-2. So it's really not a Hamiltonian, technically, but it's the important piece of the Hamiltonian. And the Coulombic repulsion would be reduced by 1 over by n well squared here. And he's arguing that this is going to be a small quantity in the limited, in fact, in which you're not dealing with point particles, but you're dealing with nuclei where there'd be additional pieces. And this is embodied in this E-nuclear piece. And also, he's generalizing the construct of saying, as opposed to dealing with a single N well, he's also sort of saying, well, you might not really need periodic order, and you could have domains, nanoscale domains, for example, that would give you this. And he's gone a step further. In conventional alpha fusion, it's not a simple tunneling argument. In conventional, when alphas come together, or even when DDs form helium-4, the reactions involve residual electromagnetic interaction. And there actually is a phenomenon. The helium-4 plus helium-4, if you think of them, if you think of the last vestige of some kind of interaction involving electromagnetism, when they're sort of in close proximity, there's a distinction between neutrons and protons. And so there's different exchange properties, and the spin degrees of freedom are different than if you just had nucleons colliding together where the identities of the helium-4 are not present. So in a conventional DD reaction, for example, you ignore the distinction between protons and neutrons. But when you get farther away, you have to include that distinction. And so this seniority pairing thing refers to this. Then now there's another phenomenon. It's called a Feshbach resonance. Now, the Feshbach resonance occurs when you can view this as sort of a reminiscent of a molecule. And if there's some residual interaction that affects the scattering, you can get a situation where when the energies of the scattering become degenerate as a result of the interaction with just a free colliding. If you have free colliding deuteron, you can picture it. The common example is they do this in ultra cold atoms. They use the magnetic field to change the scattering of the atoms that come together. And because the scattering, because it's different for heavier atoms or molecules than for normal things scattering, the two things move relative to each other, and at a certain point the energies can become degenerate. And when they do, the scattering length goes to infinity, and you can get tremendous coupling between the entities. And Talbot is basically suggesting, this is to account for the Iwamura experiments. He's basically suggesting that this is a potential mechanism and it involves some coherent coupling to the electrons in the core. Okay. Oops. Darn it. Did it again. I guess maybe he doesn't have a conclusion slide. No, he does. All right, so all it is this. He says that the N-well dependency couples the nucleus configuration to the lattice, and he's really talking about the Iwamura experiments. Okay, well, great. I can actually take a seat here.
This is work actually done when I was in Japan working with the Japanese government in the New Hydrogen Energy Laboratory, and I saw some strange observations of what I thought could be radiation as well as excess heat. This is the calorimetric cell design that I used in some of the experiments there. Others I used the flash composite Duracell design. But the important point here, the cathode is right there, and thermistor 1 is right here. Thermistor 6, the other thermistor in the cell, I call it T6, T1. And if there's radiation produced, the radiation can reach T1 going right through the coils and hitting this thermistor. If it hits the T6, it's screened by the coils of the platinum anode, and they would block it. It would not reach that probably. And furthermore, T6 is further away. So that's an important characteristic of the cell, is the conditions of Mr. T1 versus T6. Now, when you electrolyze, you evolve deuterium and oxygen. The electrolyte level falls, the electrolyte concentration increases, and so the cell voltage decreases. And running a constant current, the voltage falls with time. I ran two cells in series. This is the one that produced excess heat. This is the one that did not. With both of them, the voltage falls with time as you concentrate the electrolyte. goes down. You're running at constant current, 2.30024 amps. But the power you're putting in is going down with time. And therefore, rather than argue about calorimetric equations, you can simply say if the temperature goes up, something unusual is going on. Now, in the control cell, 2 thermistors in it also. This is how the chart came out towards you. So this is time, this is temperature, because that's the way that this is directly from the chart recording. This is the bath, this is the room temperature. But in this cell, the temperature goes down with time, as you would expect. In fact, the 2 thermistors show every little blip. They both show the same blips all the way along there. The cell that was active, the temperature goes up with time, even though the power is going down. The temperature rises. If you're in a period right here, the temperature rises. And then maybe the excess power levels off or disappears and it starts going down as you would expect. But definitely, temperature going up with time, when the power you're putting in going down with time, is difficult to explain. And you don't need calorimetric equations, it's just a simple fact. This is the same 2 cells, a later time period. Bath temperature, room temperature. This is the control cell. What I did here, I increased the current by about 20 milliamps, so the temperature went up over an hour or so. I increased the current, temperature goes up, and I turn the current back to where it was, and it goes back. Same baseline after you increase the current. And these are run in series, so the same increase in current took place here as well. But note here, again, we're seeing an increase in temperature, even though the voltage is going down. There's a rise in temperature. Then we increase the current to get this blip. And I'm going to show this later, because at the same time this was going on, we started to see a lot of unusual fluctuations in the thermistor directly in front of the anode. Anomalous temperature fluctuations. And I recorded these and then plotted them out. In this cell producing excess power, the thermistor further away screened by the platinum, nothing unusual. But the thermistor closest to the palladium cathode, you see these sudden blips in reading. I had to mark these with a red magic marker because the red line was kind of faint. But they're very brief, and by the next reading you're back to normal. So it's not a real temperature change. What I think happens is electromagnetic radiation, such as a photon, is emitted and hits the thermistor and temporarily changes the resistance, and you get an anomalous temperature reading. But it's not a real temperature change. It's just because some radiation from the cell has hit that thermistor. At least that's the theory, and I'll show that I prove this later that can happen. And again, this just shows you the one thermistor where we saw this was direct path right through the coils to that thermistor. The other one was screened and further away, and it only showed normal behavior. And we never saw this except when we were getting excess heat. Before, we never saw it. Experiments later, we never saw it. We ran control cells with the same thermistors later, and they behaved normally all the time except during these periods of excess heat. This is the actual chart recording, and I marked with a red pin where we got these strange fluctuations in temperature. This is T1 right here, the temperature with T1 thermistor. So anything above there, they're very temporarily, but a lot of them were even off scale. They just went off scale here. But this is during the period where we had the temperature rising, the frequency of these readings became larger. And later on, I don't show it here, but later on, these disappeared. I have those actual charts with me if anybody wants to look at them. This came and went, and it appeared when there was excess heat, and disappeared later when there was no excess heat. These anomalous thermistor readings. So I called the company that makes thermistors, and I asked if radiation could affect thermistor readings, and some people said no, thermistors shouldn't be damaged by radiation, but other people I talked to said, yes, maybe temporarily, high-energy photon could temporarily alter the reading. But but the themister's not damaged, it's just altered, just periodic, just for a short time period, has a fluctuation. It's not damaged at all. And so I tested this out, because I couldn't get a complete answer from the companies. And so I set up these themistors, and I would measure room temperature over a 24-hour period. And the instrument would record the high and low. So these are temperature changes each day over a 24-hour period. And the red is where I had the themystor on a radioactive source. This was a cesium-137 source, half-life 30 years, 94% 0.511 MeV and 6% 1.176 MeV. The themystor's in a glass tube, so it had to go through glass just like in the cell. But I placed it on this radioactive material, and whenever I placed it on a given themystor, that themystor read high over a 24-hour period. They're very infrequent. I'd watch it for an hour or two and I wouldn't see anything, so I just had to record over 24 hours and record the high and low. It was not nearly as active as what I saw experimentally in the active cell. But there'd be fluctuations wherever I put that themystor. I can show it graphically. The red line is the readings with the radioactive source. The other points fell close together. They almost overlap each other for the temperature change of that room. But of course, the temperature changes vary from day to day. But these are the temperature changes that should have read, and this is when it was in contact with this radioactive source. So you'd have these high readings. And this is another case that I showed you with using 5 different themistors. But the one I put on the radioactive source always gave these high readings. There were 3 exceptions. Now, 26 days, there were only 3 times it didn't give the right result. And I found sometimes you get an anomalous reading just by sitting out, because I think there's background radiation, there are cosmic rays. So occasionally you'll get a high reading just due to background radiation. But using 5 themistors, we got the right result 23 days out of 26. And previously we got the right result using 3 themistors 20 days out of 20 days, every time it was correct. What's the probability of having that happen by chance? The probability of these themistors, given the high reading when contacted with the radioactive source, 20 out of 20 correct, is this probability here, about less than 3 chances in 10 million. Using 5 themistors and getting it correct 23 out of 26 days, the probability is about 0.1 in a billion. And so you see that I pretty well proved that radiation exposure can temporarily affect the themystor and cause an anomalous high reading. So in summary, cell A produced excess power. At the same time it produced excess power, themystor T1, the one closest to the themystor with a direct path, simultaneously gave anomalous temperature excursions. Briefly went up and came right back down. The cesium-137 radiation source produced
fusion for the last 5 years, and I've found some interesting things, and it's my pleasure to share what I found with you. My presentation is dedicated to the memory of Eugene Mallow. Now, my curiosity about cold fusion began in 1999, and one of the first questions I needed to answer for myself was, how could cold fusion be real, considering it had been disproved by several well-respected laboratories? And for me, answering this question was a prerequisite to even considering the possibility of cold fusion. And the answer came by way of 9 retrospective studies I found from 13 scientists performed in the years following cold fusion's introduction and subsequent demise. Some of these analysts went back and looked at the original raw data of the work performed at Caltech, MIT, and Harwell. Some of them went to the original laboratories and interviewed members of the research teams. They found sloppy calorimetry, and they found an inherent bias in some of the researchers. And because of the pressure to quickly answer the question of cold fusion's validity in 1989, these researchers found 2 trends. Number 1, there were major errors in all of the work of these laboratories that supposedly disproved cold fusion. And second, instances of possible excess power were also found in each of these labs as well. Mike McCruber is one of the most well-respected and experienced electrochemists who's been working in the cold fusion field for the last 16 years. And he explained what happened at the Caltech laboratory. Every day they came in and they saw that the calorimetry was either producing positive excess heat or negative excess heat. And this was unbelievable to them. They didn't understand it. So they adjusted their calorimetry constant every day. And by doing so, they made their possible signs of excess heat go away. A similar event occurred at MIT. The original data shown here by the line in black indicate possible excess heat. Now, MIT made the assumption that their instrumentation was faulty, so they shifted the entire curve downward toward the baseline, making the readings average 0. And by doing so, as happened at Caltech, they made the signs of possible excess heat in 1989 go away. This data was first examined by Eugene Mallow, second by Mitchell Schwartz, and third by Philip Morrison. Morrison was a key player in the Manhattan Project, and all three of these men independently reported this undocumented adjustment to MIT. Now, in response, MIT didn't dispute that it had shifted the data. Instead, they just denied that it had any significance. Well, the consequences of MIT's cold fusion work include a very negative effect on the 1989 DOE Cold Fusion Review, and also the MIT work is used as the primary citation for the denial of patents in the United States in this field. Now, while none of the analysts who performed these retrospective reviews claimed that these laboratories showed proof of cold fusion, they did conclude that these experiments were more likely to have replicated the work of Fleischmann and Pons rather than disproved them. Now, on the other hand, I did find some interesting papers and analyses which did, in fact, corroborate the claims of Fleischmann and Pons. In 1991, Alan Bard, Charlie Barnes, and Howard Birnbaum visited the SRI International Cold Fusion Laboratory. And after performing their analysis on the work being performed there, they concluded seeing excess heat effects. Interestingly, all three of these men were on the 1989 DOE cold fusion panel 2 years prior. Now, in 1993, two scientists, Richard Garwin and Nathan Lewis, also visited the SRI International Laboratory. Garwin's one of the most well-respected physicists in the United States. Lewis was the lead scientist responsible for the Caltech cold fusion investigation. And they, too, found evidence of excess heat in SRI's work, though they only reported this privately to the Pentagon and to the Electric Power Research Institute. Some other papers that I found interesting were cold fusion studies performed by the oil companies, Amoco and Shell. I had an interest in their work considering the possible consequences to these industries by energy based on water. But unlike the work performed at Caltech, MIT, and Harwell, these scientists took their time, performed their work carefully, and they had the benefit of being very well funded. Now, when we distill the core findings of every one of these corroborative studies, we find that each of them report evidence of excess power. None of them report any evidence of major errors. The nuclear ashes that we now know to expect from the field of cold fusion were found, and three authors, including Richard Garwin, explicitly stated that the excess heat could not possibly be from a chemical origin, meaning it has to be either a nuclear reaction or some other equally new and profound effect. The next chart is a diagram of the work being performed in the cold fusion field. Work with heavy water and work with normal water. The reaction products are listed in the center. Now, we don't have enough time today to go into this chart in detail, but I just want you to know that it exists, and it can be a useful tool to quickly see what's being observed experimentally. Now, there are two notes I need to provide about this chart. First, it's very much a work in progress. This is a new field. I expect that as this field becomes better understood, this chart will also change and evolve. And also, while I did obtain general agreement from many researchers in the cold fusion field while preparing this chart, it does not, by no means indicate a consensus. There are some minor disagreements with it. It's hard to get everybody to agree on one thing. And the last chart identifies 17 different characteristics of both hot and cold fusion. It lays them side by side for a comparison. What we see is that the emerging view indicates that hot fusion will likely be appropriate for large-scale power generation, similar to today's power plants. And cold fusion energy generation will likely be appropriate at or near the point of consumption because of its small size, scalability, and portability. Now, I'd like to leave you with two questions, and before I present these questions, I realize that this is a very controversial field. I realize that there are cold fusion papers that are poorly written. I realize that there have been studies that have been performed without rigor. But from my perspective, I must ask, how likely is it that 200 men and women with strong backgrounds in science from all around the world who have been researching this primarily independently for the last 16 years could all be lying, self-delusional, or incompetent? I find that hard to believe. On the contrary, I think these people who have persevered should be honored for their commitment and their courage. Secondly, should new empirical observations be dismissed or ignored simply because they're not 100% reproducible, or because they're not well understood yet? And if not, then I ask you to consider the possibility that the results of this research may provide a new source of energy, new substances, and new technologies. I'll be happy to take any questions at this time. If there's no questions, I'll move on.
Actually, we do have time.
It was not worthy of any special funding. Since this time, numerous magazine articles and books have been written that have also repeated the same idea, that the claims of cold fusion are not believable. And last year, in December, the Department of Energy concluded its second review of cold fusion, and they too, along with their 18 peer reviewers, found that the claims of cold fusion are still not believable. So I'm going to present some myths that exist about this field, as well as some facts. Myth number one, that nothing has changed since 1989. Well, some of the facts are that a claim for anomalous energy production is now supported by numerous studies using a variety of calorimeter designs by researchers all around the world. Evidence for unexpected nuclear reactions, in addition to fusion, has been reported based on emitted radiation and accumulated reaction products. Reproducibility, using certain methods, has now reached levels normally considered adequate. There are quite a few researchers who are reporting reproducibility between 80 and 100%. And a variety of methods can be used to initiate both the anomalous energy as well as the nuclear reactions of several different types. And a rich collection of explanations is now being actively explored. Myth number two, that only a few true believers are interested in this field. Now I'm going to run through a list here very quickly just to give you a sense of the number of companies and institutions that are actively engaged in this research field. There's 8 in Russia, 2 in Ukraine, 14 in Italy, 10 in Japan, 4 in China, 3 in France, 18 in the United States, and 6 others around the world who are actively engaged in cold fusion research. Myth number 3, that the claimed anomalous energy is caused by some prosaic process or a storage mechanism. Well, every suggested prosaic explanation has been addressed, and it's been found inconsistent with the observed behavior.